Very good morning to one and all. In this video, we have to discuss Ksou, MSc second semester, chemical spectroscopy, block 2, unit 7. ಈ ಒಂದು ವಿಡಿಯೋನಲ್ಲಿ ಮಾಲಿಕ್ಯುಲರ್ ಎಲೆಕ್ಟ್ರಾನಿಕ್ ಸ್ಪೆಕ್ಟ್ರಾ, what are the salient features of molecular electronic spectra, Lambert's law, absorption coefficient, Beer's law, theory of molecular absorption, Frank-Condon principle, origin of UV visible spectroscopy, and types of electronic transitions like sigma to sigma star transition, N to pi star transition, pi to pi star transition, and N to pi star transition, and selections rules for K band, R band, B band, and E band, and some symmetry restrictions in electronic spectra. Under that, the chromophore, oxochrome. These are all the content involving in that unit 7. When that radiation passes through a transparent material, what happened? A portions of radiation may be absorbed. Some of the radiation is transmitted. As a result of energy absorption, atoms or molecules pass from a state of low energy state to high energy state. The electromagnetic radiation that is absorbed as energy exactly equal to the energy difference between the excited and ground states. Generally, this is what ground state. When electron is absorbed and shifting to the higher energy state. That is, in atomic spectra, when electrons of an atom are excited to higher energy state, the radiation that are absorbed in this process appear as absorption spectra of atoms. In similar way, electronic spectra of molecules arise when the electrons of a molecule are excited to higher energy state. The electronic spectra arises due to the changes in the arrangement of molecular electrons. The electronic spectroscopy involves the promotion of electrons from ground state to the higher energy state. For visible and UV spectrum, electronic excitations occurs in the range 200 to 800 nanometer and involve the promotions of electrons to the higher energy molecular orbital. Since the energy levels of a molecule are quantized. The energy required to bring about the excitation is a fixed quantity. Thus, the electromagnetic radiation with only a particular value of frequency will be able to cause excitations. If the substance is exposed to radiation of some different values of frequency, energy will not be absorbed and thus light or radiation will not suffer any loss in intensity. If the radiation of a desired or correct frequency is made to fall on the sample of the substance, energy will be absorbed and electrons will be promoted to the higher energy state. Thus, radiation, the light radiations on leaving these samples after absorptions will be either less intense or its intensity may be completely lost. Next, we consider that what are the salient features of molecular electronic spectra. It appears in visible and UV regions. It involves a change in electronic, vibrational and rotational energy of the molecule. They are studied both in emission and absorption, and the band show a fine structure, usually more complicated than in vibrational rotational band. All molecules exhibit electronic spectra. Consider homonuclear molecules such as here H2, N2, O2, which neither give rotational nor vibrational spectra, exhibit electronic spectra. The reason is that the instantaneous dipole moment changes during the redistribution of electronic charge accompany the electronic transition. Generally, the Lambert's law, it is clearly explains that absorptions of light. There are two laws which govern the absorptions of light by the molecule. These are Lambert's law and one more Beer's law. In that Lambert's law, when a beam of monochromatic radiation passes through a homogeneous absorbing medium, the rate of decrease of intensity of radiation with thickness of absorbing medium is proportional to the intensity of the incident radiation. Mathematically, that is written as here minus dA by dx is equal to k into I, where I is what? Intensity of radiation after passing through a thickness x of the medium. Di is equal to infinite similarly small decrease in the intensity of radiation on passing through infinite similarly small thickness dx of the medium. Minus di by dx is equal to rate of decrease of intensity of radiation with the thickness of the absorbing medium, where k is what? That is proportionality constant or absorption coefficient. Let I naught be the intensity of radiation before entering the absorbing medium, means x is equal to 0. I is the intensity radiation after passing through the thickness. X is what? That is medium calculated. That is written here. I by I naught is equal to e to the power of minus kx. Here I is equal to here I naught into e to the power of kx. The above Lambert's law equation can also be written by changing the natural logarithm to the base 10. This is what here, where x is extension coefficient of the absorbing medium and is given by A is equal to K by 2.303. Next, absorption coefficient. Absorption coefficient is a measure of the rate of decrease in intensity of electromagnetic radiation as it passes through a given substance, or the fractions of incident radiant energy absorbed per unit mass or thickness of an absorber. This is what the definition of this absorption coefficient. Next, we consider that Beers-Lambert's law. Beers' law. It states that when a beam of monochromatic radiation passed through a solution of an absorbing substance, the rate of decrease of intensity of radiation with the thickness of the absorbing solution is proportional to the intensity of incident radiation as well as the concentrations of the solution. Mathematically, that Beers' law is represented as minus di by dx is equal to k dash I into C, where C is concentrations of the solution expressed in mole per liter. K dash is molar absorption coefficient and its value depends on the nature of the absorbing substance. Suppose I naught be the intensity of the radiation before entering the absorbing solution. Then the intensity of radiation I after passing through the thickness X is written as I is equal to I naught into e to the power of minus k dash into Cx. This is the concept of what? Beers' law. Next, we look at that theory of molecular absorption. What is that theory of molecular absorption? That theory of molecular absorption. Here, let us consider the case of diatomic molecules. Diatomic molecules means what? Here, diatomic molecules like that here N2, H2, O2, these are all what diatomic molecules. If one of its atom is excited, then the molecule is said to be excited. For each of the electronic state, there is a different dependence of the molecule's energy on its internuclear separation. That is, each electronic state of the molecule has a different potential energy curve characterized by a minimum. Consider when a transition of the molecule from one electronic state to the other takes place, the emitted or absorbed radiation falls in the visible or UV regions of the electromagnetic spectrum. The electronic transition is accompanied by a number of transition involved. Rotational level of the upper and a rotational level of the lower vibrational state. This is called rotational fine structures of electronic band system. We consider in the close approximations what we are going to derive that. Here the energy is equal to sum of the all the different kind of energy, like that here vibrational energy, electronic energy, rotational energy. Here how it is written in the form of energy changes as we written here delta E by Hc, delta E by Hc EV by HC, rotational energy by HC. This is what molecular energy levels on its internuclear separations. The next concept is Frank-Condon principle. In that Frank-Condon principle, the probability of transition between two given vibrational levels of two electronic states, means A and B, is determined by Frank-Condon principle. In this principle, we have to discuss the observed transition between two states should part from extreme positions of vibrational levels. They should be represented by vertical lines. We shall now discuss how the above two predictions result from the Frank-Condon principle. The principle stems from the idea that electrons move and rearrange themselves much faster than the nuclei of molecules. Consider here simple example. We consider if one calculate the time for an electron to circle a hydrogen nucleus, then it comes out to be 1000 times shorter than the typical period of vibration of molecule. It means an electronic configuration will change in the time too short that the nuclei will not change their positions. The internuclear distance of a vibrating molecule in the course of transition between two electronic states does not change appreciably. Such a transition should then be represented by a vertical lines. These are all some operations of the Frank-Condon principle, like internuclear distance equal in the upper and lower state. Upper state internuclear distance is little less than that in the lower state. The upper state distance is little greater than the lower, and D is what? That is upper distance considerably greater. In that, the Frank-Condon principle states that transition from one state to another are most probable when nuclei are in their mean position. For example, the L and N shell. For level L and L, this is because the nuclei spend at these positions longest time on account of vibrational kinetic energy being 0 there, and also quantum mechanically square of the vibrational eigenfunctions is greatest at the extreme positions, implying that the probability of finding the nucleus is greatest there. However, the lowest vibrational energy, the quantum mechanics predicts that the most probable positions for the nuclei to remains in corresponds to equilibrium position. Thus, the most probable internuclear distance for the vibrational levels other than mu is equal to 0 corresponds to the extreme positions and to mind or mid positions. Here mu is equal to 0. It means what? The traditionals would start from extreme positions for level other than frequency is equal to 0, means vibrational energy is equal to 0. As for the latter, they would start from the what? Midpoint. Since these transitions are food probable, the corresponding vibrational bonds will be most intense. This is also one of the very important concepts, the Frank-Condon principles. It's a very important concept. Next, we consider that origin of UV visible spectroscopy. In that, UV visible spectroscopy originates from electronic transition within a molecule. This transition involving promotion of one valence electron from the ground state to the higher energy state are called what? Electronic excitations, and are caused by the absorption radiation of energy in the UV visible region of the electromagnetic spectrum. Since various energy levels of the molecules are quantized, a particular electronic transition occurs only by the absorptions of specific wavelength of radiation corresponds to the required quantum of energy. Next, the types of electronic transition. According to the molecular orbitals theory, when a molecule is excited by the absorption of energy, its electrons are promoted from a bonding to an anti-bonding orbital. The anti-bonding orbital, which is associated with the excitations of sigma electron, is called sigma bonding. So, sigma to sigma star transition takes place when a electron is promoted to anti-bonding orbital. It is represented by sigma to sigma star transition. When non-bonding electrons, that is what N, gets promoted to an anti-bonding sigma orbital, then it is represented by N to sigma star transition. Similarly, pi to pi star transition represents the promotions of pi electrons to an anti-bonding pi orbital, that is pi star orbital. Since means similarly, when an n electron is promoted to anti-bonding pi orbital, it represents n to pi star transition. N to pi star transition. The energy required for various transition obey the following order. Sigma to sigma star is greater, n to pi star is greater, pi to pi star is lesser. Here n to pi star is very less. This is what here different types of electronic transition. This is the diagram. This is electronic excitations energy. These electronic excitations energy levels. Okay. What is sigma to pi star? Sorry, sigma to sigma star transition. In that sigma to sigma star transition, this is very important questions. Please be noted down. Here it is a high energy process since sigma bonds are generally very strong. The organic compounds in which all the valence shell electrons are involved in the formation of sigma bond do not show absorption in the normal UV region. For saturated hydrocarbons like methane, propane, etc., absorption occurs nearly 115 nanometer. In that sigma to pi star transition, sorry, n to pi star transition, this type of transition takes place when saturated compounds containing one hetero atoms, unpaired electrons. Some compounds undergoing this type of transition are saturated halides, alcohols, ether, aldehydes, ketones, amines, etc. Such transition require comparatively less energy than that required for sigma to sigma star transition. Water absorbs at 167 nanometer, the methyl alcohol at 174 nanometer, methyl chloride absorbed at 169 nanometer. This saturated alkyl halides, the energy required for such a transition decreases with the increase in the size of halogen atoms. Let us compare with that here non-bonding to sigma star transition in methyl chloride and methyl iodide. Due to the greater electronegativity of chlorine atom, the n electrons on chlorine atoms are comparatively different. To exact The absorption maximum for methyl radical, for methyl chloride, here 170 to 175 nanometer, whereas that methyl iodide is 258 nanometer. Here where N is electrons of iodine atoms are loosely bound, since this transition is more probable in case of methyl iodide. Its molar extinction coefficient is also higher compared to methyl chloride. N2 sigma star transition are very sensitive to hydrogen bonding, alcohols, hydrogen bonding. Alcohols as well as amines from hydrogen bonding with the solvent molecules. Such association occurs due to the presence of non-bonding electrons on heteroatoms, and thus transitions requires greater energy. Next we'll discussing on that pi to pi star transition. In this type of transition occurs in unsaturated centers of the molecule, that is in compounds containing double or triple bonds, and also in aromatics. The excitations of pi electrons require smaller energy, hence transition of this type occurs at longer wavelength. A pi electron of a double bond is excited to pi star orbital. For example, alkene, alkynes, carbonyl compounds, cyanides, azo compounds, etc. They will show what? Pi to pi star transition. Consider an alkene. This transition requires still lesser energy as compared to N2 pi star transition. Next we consider here example of this alkene. In that this transition requires still lesser energy as compared to N2 pi star transition. Therefore, absorption occurs at a longer wavelength. Absorption usually occurs within the region of ordinary UV spectrophotometer. In conjugated alkenes, absorption bonds appear around 170 to 190 nanometer. The carbonyl bond or carbonyl compound, the band due to pi star transition appears around 180 nanometer and is most intense. That is, the value of extinction coefficient is high. The introductions of alkyl group to olefinic linkage produces a bathochromic shift of the order 3 to 5 nanometer per alkyl group. The shift depends on the type of alkyl group and stereochemistry about the double bond. The next transition is N2 pi star transition. In this type of transition, the electrons of unshared electron pair on heteroatom gets excited, means Q is equal to 0. Heteroatoms get excited to pi star antibonding orbital. This type of transition requires least amount of energy out of all the transition discussed above. The above and ends occur at longer wavelength. We consider the saturated aldehyde, so both the types of transition, lower energy means N2 pi star and higher energy pi to pi star, occurring around 290 nanometer to 180 nanometer respectively. Absorption occurs at lower wave length. Lower wave length is usually intense. We consider here absorption occurs, lower wave length is usually intense. The simple cases, it is quite easy to tell whether the transition is into pi star or pi to pi star. since the extension coefficient for the former is quite low as compared to that of later. The exact electronic structures of the molecule in the excited state is not known, but the electronic transition involves the redistributions of electrons within the molecule. Next, how the formation of this absorption bond. The radiation energy passed through a sample is sufficient to induce various electronic transition as well as transition in accompanying vibrational and rotational energy levels. We consider the figure A and figure B, that is clearly indicates that formation of this absorption bond. This is the energy curve for diatomic molecule. This is the UV absorption spectra of that aniline molecule. How to designations of absorption bond? The UV visible absorption bonds may be designated by the type of electronic transition from which they originate. For example, here sigma to sigma star and pi to pi star bonds. The following letters are used to designate the absorption bond because more than one band may arise due to the same type of electronic transition. Next, what are the properties of this band, different band? Here K bands, conjugated, that is conjugate these band originate from pi to pi star transition in the compound having pi to pi conjugated systems. For example, 1,3-butadiene. In that R band, these bands originate from into pi star transition of a single chromophoric group. For example, here carbonyl or nitro group. Next we consider B band, that is called what? Benzenide bands. These bands originate from pi to pi star transition in aromatic or heterocyclic compounds. Next we consider E band, that is what? Ethylenic band. Similar to B band, these are characteristics of aromatic and heteroaromatic compounds and originate from these are all what here the types of this E band. Next, what is that transition probability or allowed and forbidden transitions? A molecule is exposed to UV radiation. It may or may not be absorb radiation. It may or may not undergo electronic excitation. The molar absorptivity at maximum absorption is given by the expression, this one, where P is the transition probability with values from 0 to 1 and A is target area of the absorbing system, that is what? Chromophore. Hence, there is a direct relationship between the area of the chromophore and the absorbing intensity. In addition, there are other factors also govern the transition probability, maybe depending upon the symmetry and value of E maximum. The transitions can be classified. One is what? Allowed transition and forbidden transition. What is allowed transition? Allowed transitions means we consider the extinction coefficient more than 10 to the power of 4 are usually called allowed transition. They generally arise due to pi to pi star transition. This is the type of transition is a function of symmetry which in turn depend on the molecular vibration. For example, 1,3-butadiene, the absorption at 217 nanometer, the extinction coefficient is what here? 21,000 results from the allowed transition. In that forbidden transition, the value with the extinction coefficient less than 10 to the power of 4 are usually called forbidden transition. The forbidden transitions are generally caused by N to pi star transition. For example, here carbonyl compound, the absorptions near 300 nanometer with E max value 10 to 100 results from the forbidden transition. What is the symmetry restrictions of rotational electronic transition? The symmetric restrictions are, we have considered that very important point regarding that symmetry restrictions in electronic transition. The geometry of the molecular orbital in the ground state, the geometry of the molecular orbital in the excited state, the orientation of the electronic dipole of the incident light that might induce the transition. The transition will be an allowed transition if the above three factors have an appropriate symmetry relationship. Next concept is chromophore. That is one of the very important concept in this topic, UV visible spectroscopy. A covalently unsaturated group responsible for absorption in the UV or visible region is known as a chromophore. Chroma means that is color. Here double bond is there, triple bond. These are all what chromophore group may or may not impart color to the compound. It depends on whether the chromophore group absorb radiation in the visible or UV region. If the chromophore group absorb radiation, if the visible group only, then it appear colored. We consider the chromophore like here carbon-carbon double bond, triple bond having pi electrons undergo pi to pi star transition, and those having both pi and non-bonding electrons. For example, these are all the things. Since the wavelength and intensity of absorption depends on the number of factors, there are no number of set rules for the identifications of a chromophore. The characteristic of some chromophores commonly present in organic molecules are called listed here in that below. These are all what characteristics of some common unconjugated chromophore values. Here transition is also they mentioned here. Here what is that lambda value? This is what the chromophore and example. In that oxochrome means the covalently saturated group which itself does not act as chromophore, but when attached to a chromophore changes both the wavelength of the intensity of the absorption is maximum, known as oxochrome. For example, here amine, alcohol, SH, halogen, these are all the example of this oxochrome. Oxochrome generally increase the value of lambda max and E max, extinctions maximum, by extending conjugations through resonance. These are called colored enhancing group. For example, here benzene shows lambda max 256 nanometer, E max 200 nanometer, whereas aniline shows lambda max in the aniline, which is the value for that. Here both increased. Here what? Lambda max and E max both increased. Since NH2 group is an what? That is oxo. To summarize that unit, many molecules absorb UV or ultraviolet visible light. The absorbance of a solution increases as attenuations of the beam increases. Absorbance is directly proportional to path length B and concentration C. of the absorbing species. That's why that Bayes law is explained here. What A is equal to EBC, where A is what? That is constant proportionality called absorptivity. Different molecules absorb radiations of different wavelength. An absorption spectrum will show a number of absorption bands corresponds to structural groups within the molecules. The UV or visible spectroscopy is the measurement of the attenuations of a beam of light after it passes through a sample or after reflections from a sample surface. Absorption measurements can be at a single wavelength or over an extended spectral range. UV and visible light are energetic enough to promote outer electrons to higher energy levels. The UV visible spectra have broad features that are of limited use of samples identifications but very useful for quantitative measurements. The concentrations of an analyte in solutions can be determined by measuring the absorbance at some wavelength and by applying the Beer-Lambert's law. In that topics, these are all what important questions in the point of examinations, especially for that discuss the various type of electronic transition, why absorption bonds formed in UV spectrum is a broad, and what is meant by absorption coefficient, K band, R band, E band, Frank-Condon principle, allowed transition and forbidden transition. Discuss in detail about symmetry restrictions in electronic transition. What are chromophore? Give 3 examples. Observe 3 examples. Thank you. Thank you, one and all.